think I'm going to start with the introduction now. I think it's about time. Welcome, everyone. Welcome to the bsac the first seminar of the bsac Technology Seminar Series. We're starting it. This is our first talk for the seminar series. So in the seminar series, we're going to have a range of speakers from both industry and academia on topics, on really a very broad range of topics that cover what we do in bsac and related areas. We're very lucky to have our first speaker, Ashok Ajoy, today. So I'll give a brief introduction for Ashok. So Ashok received his bachelor's and MS degrees from the Birla Institute of Technology, Pilani, in India in 2010. And that was in 2010. After that, he did his PhD with Paolo Caballero at MIT in 2000 and finished that in 2016. So his PhD work was on nanoscale MRI using quantum sensors, and namely mostly focusing on NV sensors and doing nanoscale sensing with NV sensor systems, I believe. So his PhD research was already recognized early on, and he received several awards at MIT for his work, including the Manson-Benedict Award in 2014 and the Del Favora Thesis Prize in 2017. And Ashok has been at Berkeley since 2017 when he joined Professor Alex Pine's group at the Department of Chemistry first as a postdoctoral researcher, where he worked on methods of laser-assisted spin hyperpolarization for enhancing signals in NMR, so in nuclear magnetic resonance imaging. This is a technique to boost the signal-to-noise ratio. And since 2020, he's an assistant professor at the Department of Chemistry, and he works on a number of very cool topics that include NMR quantum microscopy, quantum-assisted hyperpolarization, quantum sensing and computing, and nanoscale spin dynamics. So, and today he's going to talk about some of these techniques that use optical approaches to induce hyperpolarization. He'll tell us what that is, I guess, and how that helps us improve sensitivity in these sensing experiments. Without further delay, I'll leave the stage to Ashok.
Great, thanks. Can you hear me okay?
Yeah.
Okay, excellent. So thank you, Alp, for the introduction. It's a pleasure to be here. Let me just share my screen quickly. Do you see it okay? And I'm just going to go full screen here. You can see that okay, I guess, right? Is that okay?
We see half of it.
Yeah, it's only showing half of it. Okay, now it's good.
Now it's good.
Okay, let me see. And do you see a laser?
Yes.
Okay, great. Okay, this is the wonders of Zoom. Anyway, yeah, so it's a pleasure to be here. So today I'm going to talk to you actually about this new form of quantum sensing that's called, that we're calling hyperpolarized quantum sensors. Yeah, I'd like it to be very informal. It's also a fairly short talk. Also, I decided because I've got several collaborators from bsac and several bsac alum who worked with me. So I thought today I'll speak only about unpublished work. So it's like all new stuff, and therefore may not be completely polished and so forth. It's just results like right out of the lab. But so feel free to stop me anytime you like. So anyway, so I'm going to tell you about this hyperpolarized quantum sensor. And what we're trying to do is actually make a deployable sensor that's based on NMR, or nuclear magnetic resonance. So let me just start off in a very broad sense here. Yeah, so very broadly, last few years have been exciting for several quantum technologies, and there are many systems which show these very amazing properties and high coherence times that have been used for quantum computing, including superconducting qubits and ion traps and nuclear and electronic spins. So at today's talk, I'm going to focus on not quantum computing, but instead quantum sensing, which is the ability to use these quantum systems and their fragility to detect other things, and usually detect magnetic fields. So what we try to do is to exploit the fragility of quantum systems to make them sensors of their environment. Spins are ideally suited for quantum sensing tasks because they're very sensitive to magnetic fields. So here is a picture from my colleague in Basel, Patrick Maletinsky, where he's got a single spin here on the tip of an AFM, and you can scan around here and then really be able to obtain with very high spatial resolution, spin texture, antiferromagnetic order, and so on. Several people find the NV center in diamond as a classic sort of quantum sensing platform, and I'll tell you a little bit more about it, but suffice to say, the main thing we exploit is this electron between the nitrogen and vacancy sites in a diamond lattice. And the basic principle of quantum sensing is the presence of a magnetic field. The sensor can be made to accrue a phase, and this phase will report on the magnetic field. So today I'm not going to talk about NV centers in diamond, but this will sort of form the basis of what we are working on. So I want to give you some brief introduction. The NV center in diamond, classic material. So it happens when you take a diamond lattice and you remove one carbon atom and you replace it with nitrogen, and you have a vacancy nearby. So why it became popular for quantum sensing is because of the interesting optical and spin properties of the electron. So we really are interested in the electron of this NV center. Specifically two important properties. First, that the electron can be spin polarized with light. So you apply some light, and if you've got two states here corresponding to the electron triplet, you can spin polarize the state completely to one level. So you can have all the population in one level by shining some light on it. So that makes it very powerful because it's possible to initialize the spin. And second property is that you can read out the spin with light. So the two spin states have a differential fluorescence contrast. And as they fluoresce, one state is brighter than the other. And as a result, you can read out the spin with light. So really, all the people in the world working on NV centers and allied defects, including the silicon vacancy and other defects, all work on similar properties. The fact that it's an electron that can be spin polarized with light and read out with light. And this has really given birth to these spin sensing techniques that leverage these properties. And you can ask how these spin sensing is actually performed, and this exploits the coherence of the spin. Apart from the fact that you can prepare it and read it out, these electronic spins, for instance, are very, very coherent. So suppose you want to detect a DC or time-independent magnetic field. The classic technique that's employed is to take the spin that's initialized or polarized, and then you apply a pi-half pulse. So the spin then starts precessing in the presence of this magnetic field, and the precession frequency encodes the magnetic field that it's exposed to. In principle, therefore, you can obtain a phase of the spin on a Bloch sphere that directly maps the presence of this magnetic field. And applying the second pi-half pulse allows you to convert from phase to population, and then you can read out the spin back again. So this sort of building block, very simple, it goes by the name of Ramsey interferometry, forms the basis of all quantum sensing. It really exploits the fact that if you can allow the spins to precess or freely evolve in a magnetic field for some period of time tau, then the phase that they pick up is directly proportional to this magnetic field. So the sensitivity that you can obtain is directly sort of related to the total time that you can interrogate these spins with. And this, people call this the coherence time. For technical reasons, it's called T2 star here. And the longer this time is, the more sensitive you can make your sensor. So this sort of technique, as a way of introduction, is basically the means by which you can detect a time-independent magnetic field. And you can play a similar game if you want to detect a time-dependent magnetic field or AC magnetic field. It's pretty much the same idea as before, that you allow the spins to evolve for time tau after preparing them with a pi-half pulse. But because you know the frequency at which this field is applied, you basically apply a pi pulse that's coincident with the periodicity of this field. In this case, once again, the spins will pick up a phase, and this phase will be directly proportional to the intensity of this field. and longer the time tau you can evolve for here, more sensitive you can make this sensor. So an interesting sort of property is the fact that this coherence time T2 is often longer than this time T2 star. And that's because by applying this pi pulse here, you can suppress all sources of static or slow frequency noise that these spins are exposed to, thereby making these spins only sensitive to one particular frequency of interest as defined by this period tau here and no other frequency. Hence, you can make a sensor that's often much more sensitive than in the DC mode. It's very similar to similar principles that are used in lock-in amplification and so forth. So it's a form of bandwidth narrowing, which allows you to increase the sensitivity of the sensor. So almost all quantum sensing, irrespective of the platform that's used or the defect that's employed for it, basically works on these same principles. Workhorse technique really requires you to exploit the coherence of the spins and the ability to control them. So you need to apply these pi and pi half pulses and so forth. And you can control these spins that are coherent. And if there's a way you can prepare and read them out, that you can make a very sensitive sensor. So please feel free to stop me anytime you like. Anyway, in the NV center world, this gave rise to some very interesting ideas. One of the ideas is what I worked on some years ago, and now has become a sort of very popular sort of a direction with many groups pursuing it. And that's the idea of trying to do NMR or MRI at the nanoscale. And the idea is as follows: you can take a diamond crystal and you have only one sensor, the NV center that's very close to the diamond surface here, and then you can put a molecule above it. So a molecule is made up of atoms, and the atoms usually have spin. So these are nuclear spin. And these nuclear spins, when put in a magnetic field, they start precessing. The precession of these nuclear spins produces on the site of the sensor here, again, an AC magnetic field. So you obtain a time-varying magnetic field because of the presence of these nuclear spins. And if this sensor can discriminate these different nuclei, then you can be able to do what people do in chemistry as NMR spectroscopy, but you should be able to then extract the position of these spins with respect to the sensor and then report on its structure and so forth. But it's important to realize that the basic principle one employs here is the same. The fact that you have a time-varying magnetic field that's produced by these nuclei at the site of the sensor, and you know this frequency, and then you can discriminate it.
A quick question.
Yes.
Does the molecule needs to be held stationary in space in order for the sensor to work?
Correct. So yeah, I'll talk more about it. But this is a very cartoon description. But indeed, that's correct. Yeah. There have been some demonstrations where you can actually see motion and so forth, but it's still very limited. And that's going to be the focus of my talk here. But feel free to stop me.
In traditional NMR, is there a way to extract this kind of 3D structure, and how, based on how different nuclear spins are coupled to each other?
Correct. Yeah. So this won the Nobel Prize in the 90s, where people you just by looking at these nuclear spins, you can determine completely the structure of proteins and so forth. And this often requires you to exploit the fact that the Hamiltonian coupling the spins goes only via chemical bonds. And so if you can extract this Hamiltonian, in quantum science, this goes by the name of Hamiltonian tomography. Can you determine for an unconnected graph of quantum systems, the Hamiltonian that connects them? And if you can reveal this Hamiltonian, then you can reveal the structure. And in a sense, this was accomplished in the 90s through a series of multidimensional NMR spectroscopy techniques that ultimately now you can take a protein and determine a structure, protein consisting of like hundreds of amino acids. The challenge is it's still a bulk measurement, so we have a large number of molecules, and instead these quantum sensing techniques were trying to gear towards determining the structure of few or a single molecule and its ultimate. But I have a slide here on NMR spectroscopy just for people who haven't heard about it before. So it's a very powerful and versatile technique. It's a workhorse technique that's used in chemistry, and all chemists know it. And all my undergraduate chemistry students study it as part of their coursework. And that's partly because when you obtain an NMR spectrum here, you're actually looking at different nuclei within a molecule, and the NMR spectrum has enough information to completely determine the structure of the molecule without any prior knowledge. So you can take a look, you can take this molecule, and this is actually a problem set from a class where you give them a molecule and you ask them what is R, and they're supposed to look at the spectrum and decipher what is R. So unlike mass spectrometry or infrared spectroscopy, NMR spectroscopy is very rich in its ability to kind of completely determine the structure of a molecule if you know the full spectrum. And therefore, and these, so what are we actually measuring here? So we are measuring the precession frequency of nuclei in a magnetic field. That's basically this thing. So each little peak that you obtain here is a frequency of one of these chemical groups. They are all about the same, but they're slightly different. So the important thing to note is this x-axis here. And if you see the poor pixelation, but the x-axis is in part per million. So these shifts are what's called chemical shifts. So chemical shifts reveal information of different groups within a molecule, and they are part per million of the bare frequency. So if you simply put spins in a magnetic field, the spins are processing at some frequency, let's say 100 megahertz, and these shifts are the order of 0.1 hertz, 0.1 to 1 hertz. So really, part per million shifts. But these shifts, if you can resolve them, then they have all the information about each chemical group. So each chemical group, based on its local chemical environment, has a shift that is well known and tabulated, and you can calculate it from first principles. So this is the power of NMR. Basically, you can take an unknown molecule in a liquid state, you put it in, and you can obtain the spectrum. If you obtain the spectrum, then you can tell a lot about the structure of the molecule. Another important point is these shifts, because they are part per million of the magnetic field, their absolute number increases with magnetic field. So the higher you increase the bias magnetic field, the peaks move apart more. Or if you've got these little peaks here, which you can't resolve, if you go to a higher magnetic field, they will reveal themselves easier. So you can resolve small shifts easier at high magnetic fields. And also the height of these peaks related to the spin polarization actually is proportional to magnetic field. So it is for these two reasons that everybody doing NMR spectroscopy often operates in very, very high magnetic fields. So these magnets worth multi-million dollars. So this is actually a 21 Tesla magnet here below my lab in Berkeley. But it's traditionally always operating above 10 Tesla. And for these two reasons, first, the shifts, you want the shifts to be large so you can measure them, and you want the peaks to be measurably large so you can see them. But yet, I should emphasize that this is not of a single molecule, but it's NMR of large number, Avogadro number of molecules. But when you go into these high magnetic fields and you can see these spins processing, often these detections are done inductively, so it's an RF measurement. Then you can reveal information about the molecule itself. And so that's NMR spectroscopy in a nutshell. And MRI is a version of NMR that's used for imaging, but the principles are identical.
Are the samples at room temperature in these?
Yes, all the samples here are room temperature, and that's another advantage of NMR. In this case, the samples are in room temperature in a liquid state. That's what's made them very powerful. For instance, measuring structures of proteins, etc. You can determine the structure of protein in its natural environment under physiological conditions, without crystallizing it. So there are some advantages for revealing information about molecules in their natural state. So why these quantum sensing ideas became interesting is because you can take that large NMR magnet and a large amount of sample, which is really macroscopic amount of sample. You need a test tube full of sample to see any signal, and then you can shrink it down to its ultimate limit of one molecule. And that was the compelling power that was articulated of what quantum sensors could be helpful for, really shrinking down NMR and MRI to the nanoscale. And this part of this has been accomplished recently with several groups in an international effort. So this is a result from the Harvard group, where they have a small molecule here, and they don't use one NV center, but they use a collection of NV centers. So each ball here is supposed to be an NV center, and over a 10 micron region or so. But you can see very simple NMR spectra of some simple molecules. And so what this showed, in a sense, was that you can obtain NMR from traditionally inaccessible length scales. So you can access NMR at 10 micron length scale or 1 micron length scale. And you can imagine, a lot of people got excited by this sort of enterprise because, if people interested in biochemistry, like my colleagues in the chemistry department, really want to understand how chemistry happens inside a cell, if you can obtain NMR inside one cell, then you can tell everything about how, potentially chemistry happens inside a cell, etc. And this is about the length scale of a single cell. I should mention. So,
question?
Yes.
Are these large number of NV centers, are there heterogeneity among them
so they are
up in phase?
Oh yeah, so they're all read out in phase, so it's an ensemble measurement, but their position in space is somewhat random. And all they're using here is using a larger number of NVs to get more signal. So you can increase the signal to noise and you just get a root N enhancement by using more than one NV center. So there's therefore a dynamic trade-off between spatial resolution and sensitivity. So you can say that I actually don't care to measure one molecule, because actually in practical applications, you really don't care about NMR of one molecule. For many things, you care NMR of 1 micron length scale is what's really practically useful. 1 micron to 10 micron. So you can say that I'll use a collection of NV centers in this region and then gain some signal to noise as a result.
Do you get any sensitivity from an NV that's 10 microns deep? That's as far as these spin interactions are concerned. It seems like it's really far away.
Correct. Yeah. So roughly the sensing volume that you get here can be thought of as the integration of this is about the size of this region. So, and that's easy to prove by EM theory. So it basically means that if you've got a 10 micron particle or 10 micron region of NV centers, the region of space you can detect is about 10 micron. So because you're integrating over it, so spins that are close here have a larger signal, spins here have a weaker signal, but on an ensemble average, this whole thing acts as if it was one sensor with a point spread function of about the size of this thing, which is about 10 micron. But I was going to say that while this result was very nice, it's still it's worth pointing out that this experiment was performed at a very low magnetic field. So this is like 80 millitesla. So basically, while they can see some shifts here, it is not even close to the kind of chemical shifts that one can resolve in a high magnetic field NMR spectrometer. So basically, this information here is very chemically insufficient at the moment, and that's where this field lies right now. So you can see some shifts, but it's not enough information to reveal anything about the molecule. And if you take a more complicated molecule than this simple molecule here, you would get a big blob, and you cannot resolve these peaks. And that's because these chemical shifts, they scale as part per million of the biased magnetic field, and that's the reason why NMR spectroscopy is always performed at high magnetic fields, because these peaks will move apart and you can resolve them. So while this is a sort of interesting experiment because it proves the concept of what one can potentially do, the field is at an impasse here of really resolving these peaks to be able to tell something useful from a chemistry point of view. And so, what I wanted to lay out here is roughly what the limitations of quantum sensing are for practical applications in, chemistry or chemical sensing. So the main advantage of them is that they can obtain very high spatial resolutions that are inaccessible with normal techniques. But they have some limitations. The main limitations are they are limited to low magnetic field. Okay, all experiments that you'll ever read about in NV centers are always limited to very low magnetic field, often below 0.3 Tesla. And that's because at high magnetic fields, it's much harder to control the electronic spin. So 10 Tesla, the resonance frequency of an electronic spin becomes 280 gigahertz. And this is a part of electromagnetic spectrum that's very hard to control. And there are no amplifiers and sources and so forth. So a lot of it is limited to very low magnetic field. Almost all the results in NV centers are limited to single crystal samples. And that's because of some technical reasons, which I won't go into, but the fact that you read out these spins with light requires them to be aligned in a very fixed orientation. And if you misorient them, you lose or degrade a lot of this fluorescence contrast. So if you want to operate, therefore, at high magnetic field, this requires you to use single crystals that are very precisely aligned. And you can't do this with, for instance, nanoparticles of diamond. It's also optical readout is not great in a medium that has a lot of optical scattering or fluorescence fluctuations, because what you're actually measuring is the fluorescence of these spin emitters. And if you've got them underwater or inside a cell, for instance, you get a lot of optical fluctuation that again degrades sensitivity. And ultimately, therefore, the paradigm of these NV sensing technology is more or less like this. You've got a sensor with a shallow NV, and you've got to bring the sample to this crystal of interest in order to study it. So anyway, so roughly, therefore, there's an unmet need of a quantum sensor that can operate at high magnetic field. And this is the kind of the task that my group has been engaged in the last year, trying to see if we can push this sensing technology, maintaining its high spatial resolution, but pushing it to fields that are about 10 Tesla instead of 0.1 Tesla. That's everybody else operates at. So I'm going to tell you a little bit about it. But before that, I'm just going to give you one or two slides on the vision of what we want to do with this. And we've only taken some baby steps with it, but I want to communicate, articulate what we can do with it if it's possible. One of the goals is to try to do in-cell NMR, so really NMR inside a cell. And what my goal is to try to make a version of an NMR fluorophore. So all my colleagues in chemistry, they use for biological sensing a molecule that's tagged with something that fluoresces, and then you can tell where it is based on its color. Something in a similar means, what we want to do is to take nanodiamonds, scatter them into something, and then each nanodiamond particle should reveal chemical information of its surroundings, thereby making a fluorophore, but it's actually a chemical fluorophore, and not just reporting color, but actually reporting a chemical spectrum of its surroundings. So this is a broad goal, and one of the goals is really to therefore be able to do NMR inside one cell. So you take a cell and you put these nanodiamonds inside these cells, and nanodiamonds advantageous because they can be targeted inside a cell. So you can take a cell and you can make the nanodiamond based on its coating to go in a particular location of the cell. But what we want to do is not just ask where the nanodiamond is and look at its fluorescence signature, but actually to report on some chemical information of where the particle is. And our target is therefore to be able to do NMR at a 100 nanometer to 1 micron length scale. So it's still NMR at a length scale that's inaccessible through current high field large NMR magnets. So you gain the high resolution that quantum sensors can afford you, but still be able to operate at high magnetic field. So in some sense, a high field deployable NMR sensor. And you need to go to high field because all the chemistry information is only available at high field, and you can't get it at low field. So you want to go to high field to get the chemistry information, but yet you want to make it deployable and targetable and so forth. Here's these diamond particles are. This is a picture. These are big particles, but these diamond particles are very nice because they have surfaces that you can functionalize. And there's several companies who sell you all kinds of coatings, and you can send these particles to different parts of cells and so forth. So they're biocompatible, and they're very easy to functionalize. So broadly, the goal of what we try to do and what I'll try to show you today is to try to make a quantum sensor with all these properties. First, that it should work at high magnetic field. Second, it should be deployable. So you should be able to bring it in the spatial proximity of an analyte molecule of interest. It should be able to operate at high magnetic field so that you can yield chemical sensitivity. So you get more sensitivity at high field, and you get more chemical resolution. So the analyte analyte molecules are trying to detect have just higher polarization or higher spin alignment at high magnetic field, and their chemical shifts are easier to resolve at high magnetic field. So we really want to operate at a field of something like 10 Tesla. And we want to do it in a nanoparticle so that we can take the nanoparticle and put it where we want. So you can spatially target only a particular spatial location of interest, remove chemical information only from that spatial location of interest. So you can get a high spatial resolution image. Ultimately, the goal is to try to make an NMR image of something where each pixel gives you NMR information, but in a targeted manner. So here are some other ideas of what one can do with this. So I told you about diamond particles that you can functionalize and put into cells. Here's another idea from my collaborator in Nottingham, where Melissa, she's making actually silk fibers, like electrospun fibers with diamond incorporated within them. And the goal is, once again, that you can take these diamond particles and you'll make almost like an artificial skin of some sort, and you can patch it on something. And then every particle will reveal chemical information of things that are around it. So you can obtain like an NMR sensor that you can patch on something and reveal chemical information about it. Here's another idea of what my student Adrisha has been working on, and this is trying to do NMR or chemical sensing in micro-confined environments. So we became interested in microfluidic droplets or droplets of any sort, where chemical reactions are often very hard to probe. And the idea is you take a droplet and you can put nanodiamond particles into them or on the walls of the droplet, and that through using this, you can probably study what happens of the chemistry inside a droplet or on the walls of this droplet at the interface. So, very broadly, the goal is to make, therefore, a deployable NMR sensor that works at high field that you can put into something. And so in the next 20 minutes or so, I'm going to tell you how we think we can do that. So a deployable sensor works at high field, and the sensor itself is nanoparticle or nanoscale in size, so you can get very high spatial resolution as a result. And it turns out that if you really want to make such a quantum sensor, you basically have to innovate a new sensor, because the NV sensor just does not work with these conditions. So it's still a very good sensor for the things that it's good at, which are low magnetic field, and for applications where that's okay. But if you really want to go to a field of about 10 Tesla, the NV sensor is not a very good sensor to employ. So
Ashok, I have a question about
yes.
this. Is this studied, actually, the NV properties in 10 Tesla, at 10 Tesla?
There's almost nobody who's done that, partly because, well, you can study things like you can initialize it, at 10 Tesla, but you can't apply pulses at 10 Tesla. So there's almost nobody who's operated at 10 Tesla. There's only one.
All optical control, but that requires cryogenics. You can't do that at room temperature. Okay.
Yeah, and spin control, basically, if you want to apply any microwaves, it's difficult because the resonance frequency goes into this sub-terahertz region where there's basically, the sources are like, klystrons or gyrotrons, and very difficult to obtain any broadband source in that region of high power. So it's more like an EM
let me
problem.
advertise. We will have a terahertz source talk in a couple of weeks from now.
Okay, excellent.
I'll let you know about that. But all optical control, I guess, is that something of interest, like with 2 laser pulses and using 2 photon transitions?
Yeah, it's still difficult to reveal chemical information through chemical shifts. That's because that really requires you to somehow probe the spin of the NV center. So
yeah, no, I mean all optical control of the spin.
Yeah, potentially. As I'll show you, what we are able to do is to actually obtain to actually do the same kind of things that people do with quantum sensing at low field, but at high field. And so then you can apply pulses and stuff at high field, then it becomes easier. Right, and so the main idea is that we will make a new sensor. It's not the NV sensor, but instead it's the carbon nuclear spin in the diamond that will be used as a sensor. So let me quickly tell you about its nice properties.
Before you go on, you mentioned some of your colleagues are using diamond fiber and NV sensor embedded in that fiber. Can you probe it by guided light in that fiber if you make it a single mode?
Correct. This work is not doing that, but indeed that's some of the ideas that they've been exploring. But it goes to show the power of these nanodiamonds, that you can just mix it up with the thing that you do the electrospinning with, and then you get diamond everywhere incorporated within its walls. And then we started talking, and what she's able to do with this is grow very long fibers and very low cost, so you can make fabric out of it that's incorporated with diamond. Yeah, and then if you can make a spin sensor on it, it's like a thing you can patch on something. Say you want to, crazy ideas, if you want to know if your wound is healing or not, you can stick something on top of it, and then that skin patch will act as a NMR or EPR sensor, and then you can detect how your wound is healing. It's like a non-invasively. Anyway, so I'm running out of time here. Let me quickly tell you about the main idea of how this whole thing works. So what we're trying to do is actually not use the NV center, but we'll use the carbon and diamond as the main sensor. And I will persuade you that this is actually a good idea and might work. So diamond has NV center defects. Actually, the NV center is a defect, right? It's not actually what makes up the lattice. What makes up the lattice is carbon, and carbon has a nuclear spin, which is C13. So what we're going to do is use the C13 of the diamond as a sensor. So first, it's much more abundant than the NV. It's about 1 million. So every NV has about 1 million carbons around it. Second, the carbon, unlike the NV, is very easy to operate at high magnetic field. So what everybody does with NMR any day, every day. So it's very easy, therefore, to operate at high magnetic field. So all the data I'll show you are taken at 7 Tesla. The carbon is spin half, so it's independent of orientation. So you can do it in particles, and you don't have to align it. You can just throw diamond dust on something, and the carbon always points in one direction. Perhaps the most important result is that the carbon T2, which is the coherence time of the carbons, can be very, very long. So we now approach a coherence time of 100 seconds at room temperature. So even to us doing NMR every day, this was a surprise and somewhat unexpected discovery. But the coherence time of carbons, without doing anything special, it can be very long at room temperature. And I'll show you this. So we approach something like 100 seconds. And this is the main property that we're going to exploit. They also have a very long T1, which is the time that you can hold the information in the spins for. And this is often half an hour or more, in some samples about an hour. And we're going to initialize the spin with hyperpolarization. I'll tell you a little bit more about it. And you'll read out these spins with RF, not with optics. So this is an RF quantum sensor, not an optical quantum sensor. So we'll read it out with a microcoil of some sort. But this is the main idea. So basically, it turns out that within the same diamond platform are these other spins that have these nice properties that you can make sensors out of them. I just want to tell you briefly why nuclear spins can also be good sensors. So, often people only think about electronic spins as sensors, and that's for good reason. That's because the sensitivity of a spin as a sensor depends upon T2, which is the coherence time, and gamma, which is also called the gyromagnetic ratio. It's basically quantifies how sensitive a spin is to magnetic field. And electrons have a very high gamma, and therefore are very sensitive. That's why all sensors, rubidiums, vapor cells, or NV centers are all electrons, and electrons are used because of the high gamma. And so roughly the ratio of gamma of electron to nuclear spin is 3000. So the nuclear spin is always 3000 times less sensitive than the electron as a sensor. That is generally correct all the time. But the important thing to notice is that it's a double-edged sword. So while the gamma of the electron is larger than nuclear spin, it also has a much shorter T2 for the same reason, because it's more sensitive to environmental noise. So T2 of the electron is about 100 nanoseconds. Typically, and in some of the higher density samples, even lower. So what we do is we use the nuclear spins, which I'll show you have a T2 of about 100 seconds. So basically, you can offset the loss that comes because of the lower gamma by being able to interrogate the spins for longer. And as a result, be able to make a sensor that's comparable. It's not to say that the nuclear spin is a better sensor. It's sort of comparable or slightly worse in sensitivity, but it works in a regime that currently electron spins cannot access. That is high field and nanoparticles, a regime that these new electronic spin sensors just cannot access. So in that regime, in that niche, basically, it's much better than what electrons can do. So And so this is the main idea, that these highly coherent nuclear spins will serve as the sensors. I have two short stories to tell you about it. About this, so maybe 10 minutes each, if we have the time to do so. So first, I'm going to show you how you can initialize these nuclei through a process called hyperpolarization. And second, I'm going to show you how you can actually make a magnetometer or AC field detector out of these hyperpolarized nuclei. So let me go quickly here. So what we do is these nuclei, unlike the NV center, they don't have any optical properties. So you can't shine a laser on the nuclear spins and sort of align them in a particular direction, which is what you need, because every quantum sensor needs to be initialized. But you can use the property that the nuclear spins are in the close proximity to the NV center. So you can transfer spin polarization from the NV center to the nuclear spins. That's shown in this cartoon here. Shine light on the NV center and you transfer polarization from NV to carbon. So the carbon gets spin polarized. Spin polarized only means that it's aligned and therefore produce a very strong signal, and you can read it out very efficiently. Here's a simple result of this working. I won't go into much detail, but what we do is we take diamond particles. This can even be nanoparticles, and all we do is apply laser light and chirp microwaves. So chirp microwaves are often done at low magnetic field. And if this is done, basically the nuclear spins get spin polarized because of the NV. And you can transfer a large amount of spin polarization from the NV defect to surrounding nuclei to spin polarize them. This shows the result. So this blue line here is how you normally would interrogate the nuclear spins, and you get a very crappy signal. It's because the nuclear spins are very, very insensitive, and often they're very weakly spin polarized. And so even after about 7 to 8 hours of averaging, that's kind of the signal to noise that you get to read out these nuclei. But few tens of seconds of optical pumping, and you can spin polarize them and read them out very efficiently. So we get polarization enhancements that are often about 4 orders of magnitude or higher at the field we operate at, and then they've become very efficient, and you can easily read out these nuclei, as I'll show you in a moment. It also turns out that the amount of light power you need for optical polarization is not much. So for a 1 micron particle, just about 30 nanowatts of optical power and 2 nanowatts of microwave power. So fairly easy to accomplish and polarize these particles. So we can use it for other applications. Since I don't have time, I'm not going to tell you about it, but what you can do is you can use spin polarization to make imaging agents. So we got excited by this idea, but here we put diamonds in a ring, and you can see them fluorescing optically and through hyperpolarized NMR or MRI. So you can see the same particles bright in 2 modes, and this has some applications for imaging. But it basically goes to show that these nuclear spins, which are usually very hard to see, you can suddenly see them now because you can spin polarize them. It also turns out spin polarization is very efficient. So, and you can inject spin into a material very fast by light. So if you increase the optical power. So in most recent experiments, we actually apply a lot of optical power. So about 30 watts of optical power continuously on these diamond samples. So you can polarize them very rapidly. So in 40 seconds or so, we can get close to 10% polarization, very large number on very large masses. We apply a large amount of optical power on these particles at once, of the order of about 30 watts continuously for a minute. And I won't have much time to tell you about the details, but as a result of this, we can get very enhanced optical spin polarization. That's orders of magnitude faster than you can do otherwise.
So what are we seeing in this picture? What are all these orange colors?
Right. So this is a schematic of what we actually built. But if I show you what we built, it's too complicated. It looks. Each thing here is an optical fiber which carries 1 watt of optical power. And all the fibers are arranged in a dome, and you put the diamond sample in the center of it. So we apply 1 watt from each laser, and there are about 30 lasers. The actual configuration has 42 lasers, but these are diode lasers. So, the advantage of this optical hyperpolarization is that the quality of the optical beam can be quite bad, and it doesn't matter because all you need to do is illuminate the spins. So we can use high power, low cost optical sources. So these are diode lasers, which are fiber coupled, and we shine all this light on these particles, bring to bear about 30 watts 30 to 40 watts of continuous optical power, the spins get polarized very rapidly, and we shove this polarization into the carbons very rapidly. So as a result, the growth rate of the polarization is very rapid, much more rapid than you can get through comparable other techniques which don't use light. So you can initialize, basically the main message, you can initialize the spins very, very rapidly to a very high extent.
Could you make an adiabatic demagnetization refrigerator with this technique?
Yeah, in a way, what we do is something similar, but you in a minute you get polarization that's comparable to, it's just a 10%. 10% is equivalent to, I don't know what it's like.
Millikelvins or something. Oh, but you're at 7 Tesla, right?
Yeah, so 7 Tesla, the polarization is 10 part per million. So 10% is 1 million times more. So it's equivalent to a 7 million Tesla magnet or something. So all these numbers at some level kind of look very large, but that's just because normal spin polarization through a magnet is very inefficient. If you do it through this optical technique, you can create polarization very efficiently. Anyway, so I want to go on to the main focus here in 5 minutes and show you how we actually do the sensing, which is a new aspect that is quite interesting. This was my slide again, and what I'm going to show you is the basic reason why this works is because the spin of this carbon is super highly coherent. And this is an unexpected result in our even for someone who might have worked with nuclear spins in the past. So let's just consider, if you take diamond spins or carbon or nuclear spins, you spin polarize them and you apply a pi half pulse and you look at the signal, you'll find that the signal dies very rapidly. And that's because unlike the NV center, which is a defect, these nuclear spins are actually very, very abundant, and they are in close proximity to each other. And so they are coupled to each other. So nuclear spins are always in this sort of coupled sensor limit. They are very strongly coupled, dipole coupled. So there's like small little magnets that are coupled to each other. And so you'll find that the spin polarization will rapidly die off. So it apparently looks like these spins are not very coherent. And you can ask, if I zoom into this thing, what is exactly happening? And that's basically because these spins that are coupled to each other are forming many body quantum states that are unobservable, and you're creating some large state in a Hilbert space that you cannot see. And so the spins are dead. You don't get any signal past about 2 milliseconds, right? And so then it doesn't look very favorable. You get good signal, but you can only measure the signal for 2 milliseconds. Anyway, so it turns out that through some technique, which I'll describe in a moment, it's possible to take this curve, which is called a free induction decay, which is 1 pulse and acquire, and you'll get a signal that dies in about 1.5 millisecond, and extend it to about 100 seconds. So this is slightly old data, but this shows up to 90 seconds. So the scale here is really very different. So this is milliseconds here, and the scale is seconds. This is a one-shot signal, so it's basically observing these spins continuously for about 10 minutes on this trace here. And how we do this is by applying a lot of pulses on these spins. So we apply come on a world record number of pulses. That's because these nuclear spins are very amenable to spin control at high magnetic field. So it's the same protocol as before, pi half pulse and a pulse, 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 pulse. And so we apply about 6 million pulses continuously on these carbon nuclei, and we're actually observing them continuously in the region between the pulses. This is yet another advantage of nuclear spins, that they can be observed by weak measurement. So the observation does not destroy them, unlike the NV center, which is read out optically. Here we read them out through RF, and RF measurement is non-destructive. So anyway, so we are able to read them out continuously here and obtain this trace here. And this shows the actual spin precession of these spins. So you can see them precessing for about 10 minutes. So this basically shows that the spins are very highly coherent. You just can't normally see this coherence because it's unobservable. But if you're able to appropriately control these spins, you can exploit their very long coherence. So let me just skip this slide here and then show you how you can make a sensor using this very high coherence. So we're going to do something similar. The goal is we're going to try to measure an AC magnetic field, a time varying magnetic field, similar to what a quantum sensor does, but except to do it at 7 Tesla, which is a very high magnetic field. So the idea is as follows. We apply the same protocol, pi half pulse, in a train of pi theta pulses or some pulses in some direction. And what we're going to do is observe the spins between these pulses. So these orange things are real raw data where we're observing the spins continuously every 1 nanosecond. So we're observing the spins every 1 nanosecond for about 10 minutes. We apply a magnetic field. So this is a magnetic field that you want to detect. Ultimately, this will become the NMR signal that you want to see. But right now, it's a magnetic field that you want to detect. And what we're going to do is measure this spin precession here, here, here. This is what the raw data looks like. So we're actually looking at the carbon spins precessing. This is like one-shot data in a small window here. And what we do is ultimately take this whole thing and make it 1 point by just looking at the component of the component of this oscillation at its Larmor precession frequency. So anyway, you can take this whole thing and make it 1 point, 1 point, 1 point. So you'll get 1 point per pulse. That's going to be the measurement protocol. But 1 point per pulse, but we have about 1 million pulses. So you'll get 1 million points. So it turns out very interestingly, and it's an unexpected result as well, and the theory is very rich, but if you apply no magnetic field, you get a spin decay that as before lasts for a long time, in this case, about 20 seconds. But if you apply a magnetic field, all these carbon nuclear spins are subject to a weak time oscillating magnetic field, you find this thing happen instead. Yeah, this thing opens up like a fan and you see very strong oscillations here. So this thing looks like a band now because it's very high resolution. You can't see it, but I'm going to show you in a moment. What we do is you can take this thing and decompose it into its decaying component. So a component where you only look at the signal decay and a component that looks at the oscillations. So this green thing here is just the blue graph as shown above, but you're only looking at the oscillatory part of the signal. So I'm going to cut a long story short and tell you that if you only look at this oscillatory signal, it carries a direct imprint of the magnetic field that you're trying to detect. So let me just skip and show you this result, which is the main result of this talk here. So what we've done is we apply these million pulses. We're looking between the pulses and we're getting 1 point per pulse. And these carbon quantum sensors have been subject to a magnetic field that you want to detect. And what you find is very strong coherent oscillations of the carbon-13 magnetization. Unexpected sort of result. So you flip the spins by half and the spins are locked in a particular direction. And then the spins are precessing as a result of this applied magnetic field. And this precession continues for tens of seconds, as you can see here. And if you blow up this little small window here, you see oscillations. And if you take a Fourier transform of these oscillations, they turn out to be exactly at the harmonics of the frequencies that you put in. So if you apply a frequency FAC here, you get a harmonic, first harmonic, second harmonic, and then aliased versions of the third and fourth harmonic. With a very narrow line width, the line width only given by the total time that you can measure these spins for, thereby obtaining, a few part per million like frequency resolution, but operating at a very high magnetic field. So I'm out of time here, so I'm just going to quickly conclude, but this is the main idea, and the physics of how this works is very interesting and rich. So it basically turns out that the spins undergo a secondary precession in the presence of this weak magnetic field. Maybe one last slide. What we've done here is you can track a time-varying magnetic field through the same approach. So we have here a magnetic field that's frequency dependent that you want to detect. So you operate for 20 seconds and you've got a magnetic field that's chirped or time varying. And once again, you obtain a signal as here. But if you look at little small traces of this signal that you observe for 20 seconds, you can see the frequency shift. So this is an FFT here, and you can look, and this window, the frequency is 2 kilohertz and then 2.65 and 3. So it actually is following this chirped input signal. So it basically shows that you can take this magnetometer at high field and make it such that you can track spins in or track AC magnetic fields in real time over tens of seconds. So maybe in the last slide, I'm just going to show you how this works. So we've also done a lot of experiments to uncover the mechanism of how this works. So what we're plotting here is real data, and we're actually plotting the spin trajectories of these spins on a block sphere. through some approach, which I won't have much time to talk about. But we are actually plotting in a small window here. So this is between the 4th second and the 4.1 seconds, so 10 millisecond window, what the spins look like on a block sphere. So when you have no field that's applied, the spins are locked in a particular direction, which I'm going to call X. So, and that's the reason why you can preserve these spins along this X-axis for a long time and obtain this long magnetization decay that lasts for about 10 minutes. In the presence of an AC magnetic field, however, you find that the spins actually undergo a secondary precession, which we can map in real time on the block sphere. So the spins are precessing in a secondary fashion. So if you think about it, it's almost like in the rotating frame, the spins are precessing. And what we're plotting is every point here is a result after every pulse. And through a strategy, we are able to uncover the position of the spins on a block sphere. So you can show on the X, Y, and YZ planes where they lie. You don't get the sign of Z, so you only get absolute value of Z, but you can tell where they are on the block sphere. So the basic idea is when you apply a magnetic field, spins which are locked in this direction undergo a precession like this, and the precession frequency is exactly the frequency of this AC magnetic field. This allows you to uncover what the AC magnetic field is. And thereby make a sensor that you can operate at very high magnetic fields. Okay, so let me conclude here. So our goal in my group is to try to make a spin sensor based on the same kind of quantum sensing ideas that will work at high magnetic field that you can encapsulate in a nanoparticle that you can deploy somewhere and it can reveal chemical information. To reveal chemical information, you need to operate at high magnetic field because the chemical information is not accessible at low field. And that's now you're confronted with this challenge of taking a quantum sensor and making it operate at high magnetic field. And for that, we try to use a carbon nuclear spin as a sensor, exploiting its very exquisite sort of spin coherence properties at room temperature at high field, T2s of about 100 seconds or so, and then showed that you can actually make a spin sensor out of this using the same principles of normal quantum sensing. Okay, so yeah, I have to acknowledge all the students who worked on this project. All the students in blue here worked on this project, and I thank funding agencies. So thanks, and if you have any questions, I'm happy to answer.
Thanks so much, Ashok. That was a really, really nice talk. We have a few minutes for questions. So I can start.
I have one.
Okay, you can go ahead.
Yeah, thanks for your talk. This was very nice. I have one question about using this kind of MV centers or other kind of quantum sensor for measuring the magnetic signals inside the brain. How can we use this kind of sensor to get signals instead of 10 micrometer size to have something like few millimeters?
Yeah, so the problem with the brain is mostly that you have this myelination of the axon, and the magnetic field falls. It acts like a screening for the magnetic field, and the magnetic field falls very rapidly with distance away from the presence of from the axon. So a lot of people have therefore thought about bringing to bear like nanoparticles in the close proximity that you can bring very close to the axon itself. Or to the neuron, and then be able to determine the action potential result. But otherwise, measuring magnetic fields from neurons is a difficult task. You can, of course, use an array of large sensors to kind of get some magnetic field information. This is what's done in MEG or magnetoencephalography. The problem is the inversion of these magnetic fields becomes a very difficult / impossible problem to solve. So this sort of brain helmet with a large number of magnetic field sensors you can drop on top of your head. It works to some extent, but it gives you very poor spatial resolution. And it requires an inversion problem that's very difficult to solve.
Thank you.
So Ashok, what is the first system that you would do sensing on with this platform you developed?
Yeah, so what we want to do is try to do an NMR of like 1 micron region of some small molecules, and then ultimately do it inside a cell. So I think the big technological applications of this sort of technology is really try to uncover biochemistry happening inside a cell in real time. And while this is very lofty goal, there's still not even one good way to do it, right? And so sort of a important challenge, grand challenge problem. Most people, the most current approach to do it is through optics, through fluorophores that you can either genetically engineer the cell to fluoresce, or you put markers inside the cell. What we want to try to do is to take an NMR picture of a cell at high resolution and ask at every pixel of the cell how the chemistry of the cell changes. You're looking at NMR.
So Alexander has his hands up.
Thank you for the talk. It was really great. In one of the depictions of your vision or your setup, you had something like an RF coil on the slide, like you're trying to image a cell. Would there be any benefit to having some 3D structure outside of the this one outside of the cell? In other words, like encapsulating maybe a body of cells.
All right. So yeah, exactly. The main reason is that why the setup is as so is these particles. When we use the carbon as a sensor, we actually don't read them out through light, but we actually read them out through RF. But we still use the fact that the light. So if you shine light on only one particle, only it hyperpolarizes and nothing else polarizes. So you get a signal only from this region that you optically shine light on. So you've got a coil here, you've got many particles inside a cell. So you kind of raster your beam or something, and you shine light only on one particle, and only that produces a signal which you can pick up with an RF coil. So indeed, you're right. Ultimately, the coil can be very large, but the sensing signal will have a spatial resolution given by the size of this particle. So now you can have a coil that's large. You can even have a cavity of some sort. You can have multiple cells within it. We get the spatial resolution using a laser, but we get a chemical resolution at high magnetic field. So it's like a combination of good properties of these particles at low and high magnetic fields under a laser. Does that answer your question? Or
Kind of. I was thinking of more putting substituting the RF coil for a cavity, something that you place your sample in, and would there be any benefit from actually?
Yeah. So this NMR detection, RF detection is already a cavity. It's just like not an enclosed cavity, but it's yeah. This is an inductor, but we have inside a tank circuit with an L and C, and then this is tuned to the Larmor precession frequency of the carbon nuclei. And that's how we do the detection. So all the detection I showed you was done with some sort of cavity like that.
Okay. I'll generously give myself 1 more minute for another question. What would happen if you grew diamond with isotopically purified carbon-13? So basically every lattice site in your nanodiamond or your microdiamond was an active carbon-13. Is this kind of a really messy regime? Because you show this nice trick of going from like a short T2 because of interactions to 90 seconds. Do you think those kinds of techniques would still apply even at higher densities?
Yeah, actually, this is what we are engaged in. We find that increasing the enrichment actually makes this thing better, even better, for reasons we don't understand. So let's just say that this thing was a completely unexpected. So the fact that it'll become longer is expected. The fact that it becomes so long is unexpected. And we find that enriching the crystal, that means making more carbons, makes this thing go longer. This is on a natural abundance sample, but we've done data on enriched samples, and it's sort of better with respect to the same sample unenriched. So we don't know the reasons. We don't know also the reasons why it's so long. I mean, we apply a lot of pulses, but the pulses are still spaced apart quite a lot. So it's like 10 pulses in one dipole coupling period. This should not be able to give you a factor of 60,000. So I think there's some interesting spin physics that's at play here. I think so that's kind of what we want to explore more. I think a lot of people have been focused on what sets the coherence time of electrons. It's easy to study, and people have studied this at length, but what sets the coherence properties of nuclear spins is, I think, still an unknown problem. Nuclear spins in an electronic environment, and there's certainly something here which we don't understand.
Okay, with that, I think we should wrap up here. Thanks so much again, Ashok. This was an excellent talk. and a great start to the seminar series, bsac seminar series. So I'll finish by advertising next week's talk. So we'll have William Choi from Stanford. He's an associate professor at the materials engineering department. So it'll be a talk more on the materials research aspects of energy storage and batteries. So with that, thanks to everyone for coming, and I guess we'll see each other next week. Bye, everyone.
Bye-bye.
Thank you very much, Ashok. Very good.
Thank you.
Thanks. Bye.